Now comes the fun part of lecture, because this is the earthquake hazards, how Earth wants to kill you. I actually teach another class that should be called that. It's called environmental geology. It's like everything the Earth is doing that is like trying to kill us. So earthquake hazards and how to survive them. So first of all, when an earthquake happens, everything about an earthquake, all of the bad stuff that happens from the earthquake comes from the fact the earth is moving, the ground is moving. It's moving in two ways. Of course, we have those waves, right? The energy waves, that's the shaking. But you also have fault displacement, where the rocks on one side of the fault and the other side of the fault, they move, and when they move, they can break whatever's built over top of them. I'll just show you an example of that. So here is down in New Zealand back in 2010. They had a magnitude 7.1 earthquake. The fault goes right through here. You can see what happened to those railway tracks when there is that sudden motion along the fault. However, if you are in the middle of nowhere, like you're in the middle of Kansas wheat fields and the biggest earthquake ever to happen in the universe happens, you're probably going to be just fine. You're probably going to fall over, and then the earthquake's going to stop, and you're going to stand up and be like, that was the weirdest thing that ever happened in my life, because Kansas shouldn't have earthquakes, and you're going to be fine. Because ultimately, the shaking and stuff doesn't kill you. It's all the other stuff that the shaking and the fault displacement causes. Stuff like buildings collapsing, or landslides happening, or stuff like that. So the actual shaking doesn't kill people. It's all the other stuff the shaking causes that kills people in earthquakes. So anyway, the amount of damage then that an earthquake is going to create is controlled by four main things. Of course, there's going to be the earthquake intensity. The more it's shaking, the worse the shaking is, the more damage you will typically have. Also, the duration of shaking. Earthquakes do not have a set amount of time they have to last. Some last just a few seconds, some last several minutes. And you can imagine there's probably buildings that will survive, 20 seconds of shaking, but get that up to a few minutes of nonstop shaking and they will collapse. There's also the geologic material. Certain materials amplify earthquake waves and make the waves worse. We really saw this in 1985 in Mexico City. Everyone remembers the Mexico City earthquake, at least in geology if you're old enough. But the earthquake actually didn't happen in Mexico City. It happened a few hundred kilometers away. But the reason we remember it as the Mexico City earthquake is when those earthquake waves reached Mexico City. It's built on clay and mud with a lot of water in it, and that amplified the earthquake waves, so they actually had worse damage and worse shaking than the people who were closer to the epicenter. So the material that you're built on can make the waves worse. And then lastly, there's the design of your structure. You cannot earthquake-proof a house. There's no such thing as that. But you can do a number of different things to make a structure more resistant to earthquakes. From just building it out of materials that are a little bit more flexible, to actually building your structure on shock absorbers. There are these things, it's called base isolation, and it basically absorbs some of the earthquake waves, so the building will not be damaged as much. And so there are things that you can do to design your structure to withstand earthquakes. All right, so let's take a look. First of all, we talked ground motion causes a lot of damage, but there's other things that the shaking and the ground motion can trigger that ultimately will cause death and destruction. One of these things is landslides. Landslides, landslides are not caused by earthquakes. Ultimately, landslides are caused by gravity pulling things down a hill. However, the earthquake can be that little thing that pokes it over the edge, right? That tiny little trigger that's needed to create a landslide. Now, we have an entire chapter on landslides coming up, I don't know, in a few days. And so I'm not really going to go into that much detail right now. We'll talk about it more when we get to that. Liquefaction. Now, liquefaction is one of these very interesting things that happens in an earthquake. Liquefaction occurs in water-saturated sediment. And water-saturated sediment means that all of the open space in the water, what's called the porosity, or the open space in the sediment, the porosity is filled with water. So let's imagine we've zoomed in on some sediment right here, and these circles are the sediment particles, and then in between here, that's the porosity completely filled with water. Well, what will happen then, when the earthquake is occurring and it's shaking, that allows those little sediment particles to separate a little bit, and then the water can flow through them. So what seemed like solid ground will end up behaving like a liquid for a while. And that's what they're trying to show here. The particles are moving, letting the water flow around them, and then eventually, after the earthquake, everything will settle down and it'll become solid again. Now, as a result of liquefaction, you can get these things called sand blows. This happens if the liquefied sediment is a little bit underground, like a meter or two underground. Right, here we have our unliquefied sediment layers, and then down here is a layer of sand saturated with water. That shaking turns it into a liquid, and it's going to start rising upwards, and it will erupt on the ground. And it's not like a volcano, it's not liquid rock or anything, it's a mixture of sand and water, basically erupts on the ground and creates this sand blow. Now, we saw that in New Zealand when they had that earthquake back about 10 years ago. And each one of these are little sand blows. Now, sometimes people ask me, what are the birds doing hanging out there? Well, some little worms and stuff would get caught up in the sand blow, and the birds are having dinner. That's what's going on there. Uh-oh, I said the magic word. I said dinner, and my cat wants his dinner. All right, this is some of the result of this liquefaction in these sand blows. You can see some of the sand that kind of erupted out of the ground is, in fact, starting to bury some of those cars. Now, if liquefaction happens on Earth's surface, you can get this surface starting to liquefy and move around, and heavy objects like this house can then slowly sink down into that liquefied layer of sediment. This is not quicksand. Quicksand is created in a different way. This is basically, like I said, liquefaction. And then eventually, of course, it's going to solidify again. Everything's going to settle down once that shaking's over, and now we have a fun house, I guess. All right. One of the deadliest things that an earthquake can create is called a tsunami. In fact, some of the deadliest earthquakes of like the last 20 years or so, more people died in tsunami that were generated by the earthquakes than in the actual shaking and collapse of structures. So how a tsunami is created? Tsunami is this giant wave that washes from the ocean on land. And it is created because the sea floor moves in an earthquake. So this is our original sea floor, and it moves upwards. So this whole big area of sea floor moves up. Well, the water above it then gets shoved upwards. Right? And when it gets shoved upwards, water can't stay like this. It has to level itself back out. And it's that leveling back out that creates the tsunami. Now, not all earthquakes create tsunami. We saw that seismic monitor at the beginning of the day, and you see that lots of earthquakes have happened in the past 2 weeks. Not all of those earthquakes have created tsunami. And that's because you need a few certain things to happen in order to create a tsunami. Number one, it needs to be a strong earthquake. We need basically a magnitude 7 or above earthquake. The earthquake focus also needs to be shallow, because if it's not a shallow focus, and what I mean by shallow, I'm not talking about shallow water, I'm talking about the earthquake isn't deep underground. Because if the earthquake is, 600 kilometers underground, it's not going to move the sea floor. So we need a shallow focus earthquake where the sea floor moves. And when that sea floor is shoved upwards, that's what creates the tsunami. So it has to be a strong earthquake, it has to have a shallow focus, it does have to be underwater. I mean, I didn't think I needed to put that in there, but it does. I did say a little fib. I said it has to be magnitude 7 or greater. Well, you can have a magnitude 5 earthquake create a tsunami. The only thing is, a magnitude 5 earthquake, when the tsunami washes ashore, the tsunami's like this big, so no one really cares. So what I'm getting at is, for tsunami people care about, it's got to be a strong earthquake that moves the sea floor rocks, which move the water above them, and that's how our tsunami is created. And this is a tsunami back in 2011 that is washing on shore in Japan. And that gives you an idea of just how powerful these things can be when you start looking at like the cars and stuff that are being pushed by that tsunami wave. All right, last but not least, oftentimes after earthquakes, you have a lot of fires. In fact, in the 1906 earthquake in San Francisco, more of the city ended up getting destroyed by fire than in the initial earthquake. And part of this is because we have gas lines leading to our house. Think of your own house. You probably have a water heater that runs off gas, natural gas. You might have a stove that runs off it. You probably have a furnace that runs off natural gas. And these pipes that carry this gas are underground. And look at what I showed happen to those railway lines in New Zealand. Now think, if you have these pipes underground, those can get broken. So now this natural gas will be venting into the atmosphere, and a spark of any kind could ignite that. Okay, so we have a fire, right? A fire started. You call the fire department. We just had an earthquake. They're probably really busy with all kinds of stuff going on. But hypothetically, let's say that you reach the fire department and they're like, all right, we're going to come to your house. We just had an earthquake. There's probably a lot of debris in the streets. Bridges might be down. They might have trouble even getting to your house. But let's say it's like absolutely perfect and amazing and they manage to get to your house. They're going to hook up their hoses to the fire hydrant. And how does the water get to the fire hydrant? By pipes underground. And if those gas pipes broke, what do you think happened to the water pipes? So they're going to have low water pressure. It's going to be really hard to fight the fires. So what I'm trying to get at is, fires are easily started after earthquakes. They're not so easily put out after earthquakes. So in many cases, you have some major damage caused by fires following earthquakes. All right, so this brings me then to the random picture of the day. This is out in Hammerfest, Norway, and this is a warning sign. That is the warning sign for reindeer, and underneath it, it says, "In the tunnel." So to get to Hammerfest, which is out on an island, you have to drive through this nice long tunnel, and the reindeer are not stupid, especially when the weather's bad. They're like, why hang out outside when thousands of us, well, at least hundreds, probably thousands of us can go hang out in the tunnel where it's warm and dry? And so they had to put these warnings so you didn't go into the tunnel and like run into a whole bunch of reindeer underground. So anyway, Norwegian road hazards.